Hi all. We'll be waiting for 5 more minutes. Since people are joining, let's wait for some more time. So today will be our last session of this AI Club summer school program. And today we'll be discussing about reinforcement learning, which is one of the recent fields that has emerged in machine learning and artificial intelligence. And today's session will not be streamed on YouTube. We'll be recording the session. So the people who are not able to attend today's session, you need not worry. We'll be sharing the recording on the groups and also we'll be posting it on YouTube later. So you can view that. Apart from that, I guess we have already uploaded the task 2. You can have a look at it. The deadline for task 2 is tomorrow, and we'll be uploading another task soon. And we'll be also announcing the deadline for that. Apart from that, I guess the remaining procedure is the same. For attendance, we'll be showing you the attendance QR. We have already shared the Slido Q&A page link. So you can join that to post your doubts there. And also, if you are having any doubts during the session, feel free to raise your hand so that our coordinators will be unmuting you so that you can unmute and speak. And also for the people, I guess we have already repeated this multiple times, but let me reiterate it again. So the people who have attended less than 7 sessions or who have missed more than 2 sessions, you guys need not worry. You can still be eligible to receive a certificate of completion provided you attempt the tasks that we are sharing with you. So the one of the primary reason of sharing the tasks is to provide you with a hands-on experience, but also at the same time to help you compensate for your attendance shortage. The mini quizzes of session 7 and session 8 haven't been shared yet. We'll be sharing that soon. But if you haven't attended the previous mini quizzes, then do have a look at them. All of them are still kept open. You can find the links on the WhatsApp groups and also in the announcement group. So you can attempt them whenever you are free and whenever you have seen all the previous videos. We'll wait for 2 more minutes. And if any of you have any specific doubts, you can unmute and ask, or probably raise your hand so that we give you the mic access. And also do inform your friends. So there are around, I guess, 140 attendees right now. Today will be our last session. And at the end, if you have any specific doubts about machine learning or how to explore this domain, you can ask those as well. We'll be feel free to ask. We'll be here to help you and guide you. And probably the instructors who are Meet and Pranay, they'll be also sharing some insights about how you can further proceed in this domain of AI/ML, how you can carry forward your learning in this domain. Because the summer school camp is essentially to give you a taste of the fundamentals of machine learning, but you can definitely always elaborate your experience and your learnings by exploring other stuff, by participating in more hackathons and self projects, etc. So if you're having any doubts regarding that, feel free to ask. And also regarding the certificate, I guess many of you were having doubts. So the certificate will be an e-certificate. We'll be sending you a copy of that, okay, to your registered mail IDs. So I request you all to not spam the WhatsApp groups about the uh, certification policy or whatever, okay, because we still haven't released our task 3. And let me tell you, we are also willing to ensure that most of you get the certificates. And we also want to acknowledge your activities as an attendee of this camp. So we are trying to be as lenient as possible, but still there are some policies which we have to stick to. So it might take probably another 1 or 2 weeks, because after task 2, we'll be sharing the task 3 with you, and that will be having another 4 to 5 days uh, time to attempt it and submit. After which only we can start the assessment and decide how many of you will be getting the certificates. But yeah, let me make it clear. The people who have missed more than 2 sessions, we want you guys to attempt the tasks that we have given. We are going to share with you 3 tasks. We have already shared 2 with you as of now. The second task deadline is tomorrow night, 11:59 p.m. So you need to submit at least 2 out of the 3 tasks if you are having if you have missed more than 2 sessions. I hope that's clear. If you haven't missed any sessions, then well and good. But again, we encourage you to attempt those quizzes and tasks, because that provides you with the hands-on experience and also an opportunity to apply whatever you have learned in these sessions. I guess that's all to say. We'll wait for another probably 1 or 2 minutes and we'll begin. I guess we can begin right now. People will keep joining in. Me, Pranay, you can start.
All right. Hi, guys. Welcome to the last session of the summer school conducted by the AI Club. Today, we'll be talking about another branch of AI and ML, which is reinforcement learning. All right. So, getting into reinforcement learning, the it is quite self-explanatory. So, let us first find out what reinforcement actually means. So I just searched it up online, and this is what the internet gave me. If something reinforces an idea or an opinion, it provides more proof or support for it and makes it seem true. And that's kind of the crux of what we do in reinforcement learning. We tell it if an idea is correct by giving it a positive reward, and tell if an idea is false by giving it a negative reward. And here is a Harry Potter reference for the chosen ones. So, reinforcement learning. This is quite different from the supervised and unsupervised learning that we have seen before. In supervised learning, what we saw is we give a model some labeled data, and it tries to pick out similarities and patterns between the data and labels further test data that we give it. In unsupervised learning, we have unlabeled data and it tries to find patterns in the same. But in reinforcement learning, we have an object which we call an agent, and we have an environment. And the object is allowed to explore this environment and it learns on itself. And we can say that it generates its own data. Let's not be stuck on this sentence because I'll get back to it later. But it's something quite important and to be kept in mind. It is most commonly used to solve a very different class of problems than the ones we've seen in the previous sessions. Now, all of this seems very abstract because we this is something that we've not seen before, but it has led to a huge amounts of surprising consequences. Let's take the an example of the game Go. It is an extremely complicated game, and it's been playing for like it's been in vogue since quite some time. It was made in China long ago, and the rules are extremely complicated. And yet, a robot was trained by DeepMind, a subsidiary of Google, and in 2015, it beat a professional Go player, which means it was able to capture all the complicated rules of this game and be better than a human brain. That's basically what we do in AI, and that's basically the crux of RL. It tries to learn how a human brain would learn. How we learn is we see an environment, we try to interact with it, see how the environments respond to our interactions, and modify our actions based on the same. And that is basically what an RL agent also does. Now, all of this seems very arbitrary because all of this is fundamentally intuitive. But what we want to give, if to a computer, if you want to code it out, let's say, is a stone cold rock hard algorithm that it needs to follow in order to learn. And everything that we do in RL is basically this: the conversion of this basic human intuition into a concrete mathematical model. And that is what we'll be learning in this session. So, a fundamental thing to understand is trial and error. And I think that's quite fundamental and easy. What an agent does it interacts with the environment, and through trial and error it figures out what's good and what's bad. We take in the example of a human baby, and through pain it can figure out that touching fire is bad, and the brain kind of gives it a negative reward, while milk gives it a positive reward, and it thus moves towards the milk and not the fire. It's kind of similar to what we do in RL, but in a in a much more complicated sense. Now, of course, all of to convert it to a mathematical model, we need to lay down some certain definitions. And one of these is a Markov decision process. Sounds quite fancy, but fundamentally it is very easy. It consists of 5 components. The agent. The agent is the system that we operate. For example, a robot. This is basically what we build and train, and this is what most of our focus is on. Then the environment. It is an incredibly important part of R because it is what a robot interacts with. It contains all the complexities in the real world, such as wind, friction, and all of that, and it gives us a reward. So it is basically fundamentally important for an RL system. The state. It represents the current state of the world at any point. So, of course, as we interact with the environment, things move, things change, and a lot of complicated stuff that keeps on happening. And all of that is captured in the state. Now, one important thing is the state definition should be self contained. That means that everything that we need to know about the state, we can figure out by looking at the state itself. I need not know through which path I came here or anything else. All I need to know is what this given state is. Again, depending on your environment, there could be a finite number of states or an infinite number of them. Action. These are what the robot takes to interact with the environment. For example, if I have a mouse in a maze, then it can either go straight, come back, move right, or move left. So these are 4 actions. But for example, I was, let's say, in a field and I wanted to move around, for example, in another video game, then there is an infinite possible directions in which I could move, and thus there are infinitely many actions. Thus, on the basis of the environment, we decide what actions we can take. And reward. It's what I keep on referring to, and it's one of the most important things in RL environment. It is the feedback that an environment gives to the agent. Without it, there is no point of our reinforcement learning because it is what tells if an action is good or bad and how good it is in comparison to other actions. Favorable actions lead to high positive rewards, and bad actions lead to highly negative rewards. We can kind of understand that we would want a lot of reward, and that's what agents try to do. They try to maximize the reward that the environment gives to them, and of course, they do so by optimizing their actions. It's time for attendance. So you all can scan the QR code and fill the form. I'll give you around 2 to 3 minutes to. All right. I guess we can move on now. So one thing I would like to focus on is the environment because it is very important thing to understand perfectly. It so the environment is what the agent interacts with, and the environment is what gives you your rewards. It gives feedback based on a certain action, and that is what influences further decision making. So I guess you can see these three images that clearly distinguish supervised, unsupervised, and reinforcement learnings. In supervised learnings, we input features and their labels, and it is regularized by the loss function and gives out predictions, as in labels for more features, for training feature, testing features. In unsupervised learning, all we input is the features and it finds out patterns in data on its own. But on the other hand, in reinforcement learning, our input is the state that we're currently in and the action that we decide to perform. And on the basis of the reward that the environment provides to us, we change our actions accordingly. And after a lot of training, final thing that we have is the best, most optimal action we can get to get the highest possible reward. Again, another important part is rewards, and it's of vital importance that you understand these. Now, thing is, I keep talking about these rewards as if these are something that we can control. Because if there can be two potentially rewarding situations, but there is one that is better than the other, and thus not only the sign, but even the magnitude of the reward has a lot of importance. Thus, there has to be a good amount of thought put in before we decide the rewards in any environment. Again, for a maze, it's quite obvious that we would like to not bump into a wall. Thus, doing that as an action would lead to a high negative reward, and reaching our goal would lead to a highly positive reward. Now, these exact magnitudes are something that they are not exact, and something that we do not have to consider, because there are a lot of environments that have been provided to us that simply have all of these coded in. So all we have to do is load an environment from an online available set of environments and train our agent in this environment. Our job is quite simple then, because we don't need to put in a lot of thought into how the environment is giving out the rewards and what reward it's giving out. All we think is that the environment magically gives out a perfect reward, and all we have to do is control the agent. Now that I've introduced you to all the components of a Markov decision process, let me take you through a simple example to get a better understanding on this here. So I'm guessing all of you would have played a game of tic-tac-toe or noughts and crosses. So in this, we would define every part of the MDP as follows. So the agent would play against the environment, the opponent. So whatever coins we place would be basically the agent placing it, and the opponent placing their own tiles would be the environment doing the same. The state of any point is the current position of all the tokens, not the tokens of the opponent, not just our tokens, all of them. And it's quite evident that if we have a picture of all the tokens on the board, we don't need to know what the previous actions were. We can purely think from this given point onwards, and which is why it is important for states to be self sustained and not requiring a history of the actions. Now, again, there are 9 possible squares, and thus the agent can put their token in any of the 9 boxes. So, in this particular example, let's say that the agent gets positive 10 points if it wins, and negative 10 points if it loses. And an intermediate move gives a neutral reward of 0, because any intermediate step would not necessarily give us an edge. This image is very helpful in finding out and understanding what an MDP does. So let us say that the initial state has been determined. This initial state, the opponent has placed a token in a particular place, and that has been passed to us. Now, us, the agent, will look at the possible places where we can keep a token, and based on probabilities, decide which action to take. After it takes this decision, this action is passed to the environment. The environment then processes this action and figures out what to do next. The environment here has two jobs. It provides us the reward for the action we have just taken and transitions to the next state. So right now it's an intermediate action, so we would get 0 rewards. And on the basis of, again, probabilities, the environment will transition to a next state, as in place a token in another place. And this cyclical thing will go on and on until an end state has been reached. And again, all of this is quite intuitive, but all of this has now been given thorough, concrete definitions, and thus we can now proceed to a more rigorous algorithmic way of defining the same. Now, one thing we need to understand is what a time step is, and another thing is what an episode is. So, from a state, when the agent takes an actions from all the possible actions, and passes it to the environment, and the environment gives us back a reward. This one cycle is called a time step. So we can understand that this time step keeps on happening and happening and happening, and thus it iterates over all the time steps. It goes through each and every time step until it reaches what is known as a terminal state. This terminal state is a state after which no more moves can be made, and is thus the end. And reaching this terminal state signals the end of an episode. After reaching a terminal state, again it goes back to the beginning, chooses an initial state, and does the same. And this is basically how it generates its own data. It takes a state, provides an action, gets a reward, and in a transition to the next state. This is basically its own, can be thought of as its own data generation. And the sequence of time steps can be represented in the following way. It was in state 3 out of all the states. It did action A3. It got the reward R4 and it transitioned into state 4. Now in state 4, it chose action A4 out of the available actions and it got a return R5 and transitioned into S5. Again at S5, it chose action A5, got a reward R6 and transitioned into S6. This trajectory keeps on going on and on until the terminal state. Again, these transitions and these action, the choice of the action are something that is based on probability and it's not something fixed or understood. Again, I keep talking about the terminal state, but it's not necessary that every task has a terminal state, so it is helpful to make a distinction. There are a few tasks which are called episodic tasks, where there is a well defined end or terminal state. And in these tasks, of course, an episode makes sense, and each round is called an episode. Again, after an episode is done, when we go back to the beginning and start acting again, then this second iteration is completely independent of the first iteration. And yeah, so each independent is independent of the other. In continuing tasks, they have no end. And they can go on and on forever until the system is stopped manually. Example would be a robot managing a process. For example, in an automated industry, if there's a robot performing a certain task, then there's no end to it unless we shut down for the day and manually stop it. So it keeps going on, and there is no exact terminal state for it. Transitions. Now, this is something that we need to have addressed before, but it's something we need to understand very well. So, given a state, the agent's job is to choose which action to take. So, on the basis of probabilities given to it, it chooses a plausible action. This action is given to the environment, and the environment's job is to decide the next state. Again, these states are based on the basis of probability. So if you see this picture, in S1, let's say there are two possible, of course, there are more than that, but let's say there are two possible actions. A1, placing it on the green arrow, or A2, placing the X on the blue arrow. And the agent is free to choose any one of these. Let's say it chooses A1. Then it gets reward A3, R3, sorry, and the environment chooses whether to transition to S2 or to S3. Again, if it chooses A2, then it would, to generalize, it would get a reward R4. But since we know R3 and R4 are both 0 in this case, so R4 is equal to R3. And thus it gets the reward R3 and makes the choice of transitioning to either S4 or to S5. Thus the agent determines the next action, and given a state action pair, the environmental job is to decide the next state. Now that we've talked about all of this, what do we do? Like I told you before, the environment gives us everything we need. It gives us an environment, the possible tasks, and the reward. What we do is we train the agent. We train the agent such that it is able to pick the best possible action at each possible state. That's basically what we humans do, right? If we are provided a certain opportunity or a certain dilemma, then we analyze each action carefully try to figure out which would be best for us, and then we take that action. This is basically what we have to do in an RL situation. Again, now we need to understand to further proceed three topics: the policy, the value, and the return. Again, these are fancy names, but as we go further, we will realize that they're quite straightforward. In fact, let's go to the return. So, it's quite obvious to us that we need to think in the long run, that immediate pleasures are not the best thing, and if we get a higher pleasure later on, then that is better for us. For example, let's take a game of chess. Let's say you eliminate or capture someone's bishop. Alright, that's good because they've lost a piece. But then in the end, if you're losing your king, then that temporary reward is of no value. Thus, we need to also consider further rewards and not just the reward that we get in this certain step. Thus, for each action, the reward is not as important as the return, which is the sum of all the rewards that we keep getting. But of course, if for long episodes or continuing tasks, this will return tends to be a huge value, and thus we introduce a discount factor gamma. The, the discount factor is multiplied in powers to each successive return, and then this reward, and all of these are added up to give us the return. Thus, for a task which has n states from the current state, we get the return to be R naught, the reward right now, plus gamma times R1, plus gamma square times R2, plus so on, plus gamma power n times Rn. Now first, we get this for a certain state action pair. So let's say at a given state, we decide an action. So we'll get a return for that. And from this time on, if we decide a way to choose these actions, then the returns that we get is what we consider in the return. So now we do things, usually we try to keep this gamma less than 1 such that the return does not grow infinitely. Thus, of course, because of this gamma factor, we can see that the immediate rewards are more valuable than the further ones. Of course, like I showed you in the chess example, the end reward was much, much more important, and thus the reward for that should be significantly higher so that it can be larger than the gamma power n term that will be multiplied to it. All of these comparable magnitudes of reward are coded into the environment, and again, we don't need to consider them a lot. Again, so now we don't look at the reward, we look at the return, because rewards that lead to the highest total return are obviously better than the ones that are just temporarily very high, but further on decrease a lot. Now time for a quiz. Please scan the QR code and get the quiz started. If you're not able to scan the QR code, then you can just go to the slider.com and write this number, and you'll be able to join the event. Alright, so I guess we can start now. Now, this requires an intuitive understanding more than a very perfect reward understanding. I'll keep the quiz open for some time. Alright, I think we can move on. Alright, give me one more minute. Alright, so there's been a lot of people giving the answers C or D. That is, I think all of us can agree that we would get a positive reward for reaching the destination, so a plus 10 for that, and minus 5 for walking into work. That's quite bad. But the confusion being where the reward we should get when we walk into a valid empty cell. Now, the answer is actually option B, that is minus 1 for moving into a valid empty cell. Now, that's slightly confusing because walking into a valid empty cell is not necessarily a bad thing, right? But the question says that the aim is to find the optimal path. That is the keyword over here. Because let's say it got, let's say, 0 reward for moving into an empty cell, then it would not consider it as a bad thing. And let's say it kept moving front and back, and front and back, again and again and again. So it's not the best path. It can take a longer path and have the same reward and find no problem in that. Again, for a plus 1 for walking into a valid empty cell encourages it to take a longer path to reach the destination. And that's not really what we want, right? So we want a slight negative reward, but not too high of a negative reward. Thus, minus 1 is, again, all of these are estimates, but what I wanted to emphasize is that a negative reward for making even a valid step is kind of important to get the optimal path and not just any path. Now, this might seem arbitrary, but this is the case for pre-downloaded environments available online too, in which for maze solvers, some of them give a negative reward for walking into an empty valid cell. So yeah, that was congrats to Ravi. Now I guess we can go back to the presentation. Now, I think I would like to get back to the fact that we were discussing policy, value, and return. We had discussed what the return was, and now we will move on to policy. Policy is essentially what we need to find in an RL situation. It is a strategy that we follow to pick an action. I always keep saying that given a state, the agent figures out what the next state is. But how does it do that? The policy is what determines and tells the agent to pick the next state given a certain the action given a certain state. Sorry. Now, for each state, an action, each state is assigned a particular action, or each state and an action is given a certain policy. When I was discussing returns, I told you about how at a given state, when we move to the next state with a given action and then followed a certain way of choosing the next state from that given action, then we would get the return. Similarly, over here we make what is called a lookup table. This is called a lookup table. So over here, let's assume that we have four possible states and three possible actions that we can take per state. Thus, we can assign each of these probabilities. Given this notation is something that we use in probability, where A bar S is probability of A given S. So by A1 bar S1 basically translates to the probability of taking action A1 given that you are in the state S1. So from this lookup table, we can write down all the probabilities. This would be probability of taking A1 in state S1, A2 in S1, A3 in S1, and so on. We can populate this table. Now I'm saying it as if we already know these probabilities, but we don't. That is basically what we need to find. So over the process of learning, which Neith will talk about, we will get better and better at finding these values of pi and filling this table up. And in the end, we will have the perfect table that we need to, work with the environment. So one more thing that I would like to talk about is, yeah, I guess you've seen how in a neural network we find the weights essentially, the weights in the biases, and we start off with initializing them. So over here also we can initialize them in any way, but one thing we need to keep in mind is that these are probabilities. So the sum of probabilities in each row has to be one because it does take some action, right? So the sum of probability of taking A1 given S1 plus A2 given S1 plus A3 given S1 equals 1. So when we're initializing these, we need to keep that in mind. Okay, now let's say that a very simple and a very crude maze solver can be thought of as follows. Just take a left wall and just stick to it. If you keep following the left wall, you will end up the reaching the end. That's one thing, one way. It's not a very efficient way, but of course that is a way. And in that case, we always take the choice of sticking to the left wall. So this is kind of a deterministic policy where you always choose one action over the other. And thus for that, the probability of choosing that is 1 and the probability of choosing the other is 0. So pi of a1 in this image, pi of a1 given s1 is 1 and pi of a2 given s1 is 0. If you didn't understand the wall example, then it's fine. It's a very standard example, but it's something that can be overlooked for now. But the point that I was trying to make is, in some situations, it is necessary to pick one action over the other, and thus some policies can be deterministic. On the other hand, it's not very advantageous to have a very fixed policy. Example, if you're playing a game of chess, let's say, then again, having a very fixed and rigid policy can lead to others realizing your policy and beating you very easily. And thus, element of probability is required. And over here, the actions are chosen based on a probability, and this is known as a stochastic process. Stochastic policy. Sorry. Essentially, we can see that the deterministic policy is kind of an extreme case of the stochastic policy with pi equal 1 for one action and 0 for the rest. Value. Now, value is a very important thing in RL, and thus it's essential that we understand this very properly. Now, like I said, that the environment chooses which state to take, again, based on probabilities. So we are not always sure that if we choose a policy and stick to it, we will get the same return. Because of course, if in one time the environment transitions to state S1, let's say, and further on with this policy, it will get back a state of rewards, but a set of rewards, sorry. But in another case, let's say if I do the same action, it might transition to a different state. And in this state, if I keep following the given policy that let's say we have assumed for now, and keep following that, then we will get a very different set of rewards, whose sum will of course give a very different return. So of course, these are different, and thus we need to kind of average them out and see what kind of the average return is from a state when we perform a certain perform actions on the basis of a certain policy. This average value is known, this average reward, this average return is called the value. Let us look at this lookup table, because lookup tables are a very handy way of keeping track of everything. So at S1, if we follow the policy pi, let's say, then we would get a value V1. This means that if we start off from the state S1 and keep choosing actions on the basis of a policy pi. Now, the policy pi kind of seems arbitrary, so let's give an example. Let's say a policy pi could be always take a right, or always take a left, or choose the action that gives the highest reward, or choose the action that gives a negative reward. Of course, that is a very absurd policy. But just for example, these are what policies kind of look like. And let's say given S1, we choose this policy pi, then the average return that we get is V1. For S2, it would be V2. For S3, it would be V3. And for S4, it would be V4. This V is for a certain state. It's the characteristic of a state and is thus known as state value. Again, this is the average return over many episodes, because in each episode, the way the state transition happens is not a determined thing, and thus we need to average it out. Another thing that we'd like to look at is the Q value, that is the state action value. So let's say at a given state S1, if we take an action A1, and after taking this action A1, we continue to choose actions on the basis of a policy pi, then the average return that we get, that is known as the state action value. It is a characteristic of not just the state, but also the action that we have taken in that state. In the previous example, all we cared about was the state, and immediately after getting into that state, we followed a policy pi. Over here, It is quite different. Where at a state S1, we first take the action A1 and then choose a policy and then act based on the policy. Why this is important and much more important than state value is something that we'll be able to understand later, where we learn pew learning, which Meet will talk about later in his session. But essentially, over here, we have one more, you can call it a degree of freedom, where we are able to vary the first action that we take before we choose the policy by. So it gives us more freedom and thus more chances of getting it right. You can think of it. Thus, this value v and the q value q are very important parts of RL, and it's essential that you understand these properties. It's time for quiz 2. Y'all can scan this QR code and join the Slido. Please note this is different from the previous Slido QR, and you'll have to scan it again to join. Alright, so I think we can start now. This is fairly straightforward as a question. Which component of RL is responsible for mapping states to actions? If you're new to the word mapping, you can kind of think of linking a state to the action, providing a connection between them. I think we can take another minute. Alright, so I think most of you have answered. I think we can move on. So there seems to be an equal clash between policy and the value function. Well, no one's even model, so that's it. Uh, the correct answer is policy because the question stated that we want to map states to actions, which means given a certain state, we need to choose an action. And that is basically the definition of policy. Value function matches maps states and the rewards. Sorry, to be precise, the return. Because given a state, what the value function, the lookup table in the value function gives us is the return that we get following a certain policy. But the policy is the one that maps the states to the actions and decides on what basis we choose a particular action. So, congrats, Sri Charan. Everyone else who got it right. People who got it wrong, don't worry. There's always a chance to improve. This was just to test your understanding. Now we'll talk about solution categories. Before that, I would like to just add a small point that after seeing all of this, it's quite obvious that given a certain situation, what a model needs, what a agent needs is the current state, the action, the reward that it got, in the next state. That is one time step. And I think if you've learned Python basics, then you know what a tuple is. So we store these, the current state, the action, the reward, and the next state in a tuple, and we pass it on to the agent. So while coding RL environment, coding RL agents out, this tuple is quite important and is thus stored in memory. And now solution categories. We have model based. These are quite rare. These assume that we know the internal operation of the environment, which means that given a state and given the action, we know for sure what return we will get and with what probabilities it's going to transition to the next state. This is something that we assume we know perfectly in a model based system. And like from what I've talked about before and like understanding how complex environments get, it is quite common to think that model based situations do not come around very often, and that is true. But training an agent in a model based environment is known as planning because you know what reward you're going to get and how it's going to transition to the next state. And thus, you can simply plan what you're going to do and what policy you want theoretically without actually even interacting with the environment. These are model-based systems, and model-free systems are the ones that we have a fairly intuitive understanding of. in which you don't know anything about the rewards and the transitions until you actually interact with it. Even when you do, you don't understand the internal mechanisms, you just assume that you magically get the next state and the reward. You treat the environment as an external black box, and all the internal happenings is something we don't concern ourselves with. All we care is the return that we somehow get and the next state. And this is one sort of classification. Another, not very important classification, and honestly, something that we don't need to focus too much about, are predictions and controls. We will again mostly be dealing with control problems, but because the term exists, I'll just introduce you all to it. In a prediction problem, we have to find the value given a certain policy. We don't encounter this much, but let's say we have a policy given to us and we have to find out the value function associated with it, then it's called a prediction problem because we have to predict the value. Again, quite obviously, that is not what we usually deal with in an RL environment. Control is what we usually find where the agent explores the environment, the policy space it can be called, and finds the optimal policy. This is a nice way to think of the environment as a policy space. Environment is just a collection of possible of policies, and we need to explore that to find out which one is the best suited for us. Thus, evidently, most of the problems we deal with are model-free control problems. Model-free because we don't know a lot about the environment, and control because our agent explores the environment to find the best possible policy. Again, this is kind of just a recap of what we've learned and understood from before. We don't have an understanding of how the environment reacts, and the agent can only gain this understanding by interaction with the environment. Thus, it takes actions, gets the rewards, and tries to better its actions based on these. If it gets a highly negative reward, it, like a human brain would, thinks that, okay, I'm not going to do this action anymore because I got a highly negative reward. I'm going to try to focus on improving my rewards and more specifically my returns so that I can kind of find the optimal way to interact with the environment. This learning is on the trial and error basis because it can't know something, it cannot know the rewards and the value unless it's tried going in that path. Again, I think I've told this before, but we can think of going through a trajectory as in generating its own training data. Now, a little bit of math that we will delve into. Because right now, well, most of it has been quite theoretical, but we have not delved into too much of math. So, the Bellman equations, these are quite intuitive and recursive relationships. It, if for people who don't know what recursive relationships are, it is when a certain entity is expressed in terms of the same entity in a different state. I'll explain that in a bit. So Bellman equations come in three possible forms. One for the return, and I will explain it in a little bit detail now, such that you can understand the other two forms fairly easily. It is quite intuitive, but I'll go through it just the same. So return. Do we remember the mathematical form of return, right? We have R naught plus gamma R1 plus gamma square R2 plus gamma cube R3 plus so on. Now, let's say in your head, or like take a piece of paper and write this equation down. Just I'll give you a minute because it's easier to understand if you have the equation written in front of you and not arbitrarily thinking in your head. So take a piece of paper and write down return as R naught plus gamma R1 plus gamma R2 plus gamma square R2 plus so on. Now let's isolate the R naught term and consider the rest of this equation. gamma 1, gamma r1 plus gamma square r2 plus so on. Let's say there is a factor common of gamma in all of these terms. So let's just take it outside and we will get gamma multiplied by r1 plus gamma r2 plus gamma square r3 plus so on until gamma power n minus 1 rn. Now this term in the bracket is very evidently the return that we will get when we start from state R1, that is after we have a state R2, after we have already taken an action and reached the next state. So it's thus when let's say thus it and thus this can be expressed as a return. So now the return from the initial state can be expressed in terms of the return from the next state. This is known as a recursive relationship because we are expressing return in terms of return. The explicit equation would be the return that we get from the original state would be equal to the first return that we get, that is capital R1 over here, plus gamma times the return that we get from this further state. So writing it down, when capital G is the return over here, when we write it down, we would get G1 equals R1 plus gamma G2. Kind of intuitive, right? Because if you think about it, if you're just isolating the further steps, discounting that return and adding the initial return, you should get the initial. And sorry, adding the initial reward, you should get the initial return. Again, now this is not just for the first state, right? This can be generalized for any state. For any state, if you start with a reward and add to it a discounted return from the next state, then you would get the state the required return. So let's say at a given time step t, we would have g of t, and that would be equal to r of t, that is the return from that, the reward from that state, plus the discount factor multiplied by the return from the next state. G of t equals r of t plus gamma g of t plus 1. Fairly intuitive and very powerful. We will be using this extensively in the further session. Again, very similar to the previous equation of return, we will have the Bellman equation for state the value or the state value. I hope you remember what value was. It was the expectation, it was the average value that we would get over many iterations and many episodes. So of course, if we can have a Bellman equation for the return, then why not have a Bellman equation for the state value? And we can kind of think of taking this previous equation and just averaging it out over many time steps. So if we average the left hand side, we will get the value v given s1, and this e is the expectation value. Now expectation value is a huge deal in mathematics, but I'll just explain it briefly. It's quite understandable that it is the average value given a probability wise weight. So if something has a higher probability of occurring, then it would obviously have a higher weight in the mean. And if something has a lower weight, lower chance of occurring, it would have a lower weight in the mean. For example, let's say there is one particular action which has a very, very low probability but a very high reward. The amount of weight, the very high return, let's say, then the amount of weight I would give to that return would be in proportion to its probability. And if there's a moderately high return giving action, which has a very high probability of occurring, then I would give that a higher priority and I would take their weighted mean. This is kind of the intuition behind an expectation value, and that is what we write on the right hand side. So expectation value of the first return, because again the return need not be same. Usually we take it to be the same, but just for a more rigorous mathematical way of understanding it, we would take the expectation value of the first return followed by the again the value of from the next state times gamma. It is basically taking this equation and just averaging it out over many episodes. Quite straightforward. And that will give you, and if you take the general form of the previous equation, you will get this equation. V of S of t equals expectation value of R of t plus gamma times V of S of t plus 1. That is the value that I get when I'm in state S of t equals the expectation value of the immediate reward from the next action R of t plus the discount factor times the value from the next state S of t plus 1. Now again, we have dealt with the return, the state value. We have one more thing left that we've already discussed, that is the Q value, state action value, right? And of course, if we can have a Bellman equation for these two, of course we can have one for the state action value. It is the intuition is exactly the same, except there is one more thing to consider. That is taking a state, and also an action, because Q depends on two things. We have 2 degrees of freedom, an action and a state. So you can see that the Bellman equation looks exactly the same as the previous. Q of S1 comma A1 equals E expectation value of R1 plus gamma times Q of S2 A2. And to generalize at state T, the state action value at that state equals the expectation value of the immediate reward plus a discounted state action value from the next state. And all of these are seem kind of arbitrary because all of these describe the situation well of what we are trying to solve, but it's not an algorithm. And this, but all of these are integral parts of finding an algorithm, and thus they have to be explained in great detail. Now I'll hand over to Meet, who will take all of these, assimilate these, and give you a stone cold algorithm for solving RL equations. Thank you.
Hello, guys. So great job, Pranay. That was very informative. So taking over from here, we have already discussed what are the basics of RL, right? Like the definitions and the different terminologies. So now we'll be discussing of what we actually solve RL problems, right? So let me just share my screen.
I would like to add something. Although we are on MS Teams, the attendance link is for everyone. So even though you're on MS Teams, please do fill the form for attendance. It will be shown again during the session. Guys, we have run into technical issue. Please give us 5 minutes. We'll rectify this now. Until then, I'll take up a few doubts. I think Kavita had a doubt. I'll unmute you. You can ask your doubt. Kavita? Do you have a doubt? Alright. Vignesh, did you have any doubt? I've allowed you to unmute if you want to ask. Sugantha? Okay. Pankaj Kumar? You can unmute your mics and ask any doubt that you have. Alright. Kavita, you can unmute your mic and ask your doubt. Sorry, I can't hear you. Maybe you can write it on the chat. Alright, I guess we'll start off with the next part of the session then. I'll hand it over to me.
Hello, am I audible? Cool. So, um, yeah. So we'll be starting. Due to some technical issue, Pranay will have to share the PPT. So we'll start with why do we need, I mean, what do we do to actually solve an RL model, right? RL problem. So now we have just discussed all the terminologies and stuff. So now we have to focus on the algorithms which we can use to actually solve those problems. Now here I've written algorithms to solve an MDP. What MDP essentially is a Markov decision process, obviously, which Pranay had discussed. So moving on. Okay, so what do we actually even mean by saying solving an MDP? So basically, we need to find an optimal policy so that our agent will know where to move and which action to take at which particular state, right? That's what we had discussed. So that is basically what we want to achieve. Now, how do we find an optimal policy? To find an optimal policy basically means choosing the action which you think will give the best return, right? So basically an action which will give you the best and we know that return can be specified in the way in terms of state action value and state value, both of them, right? Q values and state values are denoted by v. So we can use those two if we know the state action values for all the state action pairs or the state values for all the states. We can essentially compare the values and check which state has the best value and take that action, right? So basically either we should have an optimal policy with us or we should be having an optimal state value function with us, right? Which says for each particular state what we should be using. Now, so how do we actually calculate the expected returns? We can't sit and try each and every action, right? Because there can be many actions, there can be many states. So we can't just keep adding or doing stuff like that. So what we can actually do is, as Pranay had discussed, we can use something called recursion or dynamic programming. So what recursion basically is finding the value of a particular function or any value of a particular term using terms which had already been discussed, basically using terms which had already been used. So if I have, for example, you can say about Fibonacci sequence. I think everyone would be knowing what a Fibonacci sequence is. If you don't know, it basically is a sequence. It's like a pattern of numbers where each number is the sum of the two numbers before it, right? So now if I have to find the 100th term of the Fibonacci sequence, it'll take a lot of time for me. But if I know the 98th and the 99th term, I can easily add those two and find the 100th term. So basically, that's what we'll be doing here. Instead of calculating each and every reward, which is basically impossible for a huge model, we'll be using recursion. We'll be using values which we already know, and in terms of those values, we'll be calculating the next value. So moving on. Yeah. So a quick recap about what we had discussed. We have model-based and model-free methods. And what exactly are those? We know that model-based methods are used for a particular model of which the entire logic you know. For example, if you know to how to play chess, you can decide, okay, this action will lead to this state and it will give me this reward, and the chances of this happening is this much. So you know all of that, right? So in because you know the game of chess, so that is what is called a model-based method, right? And in case of model-free method, you have suppose you are a toddler and you have no clue what chess even is. You just randomly place tokens, the pieces wherever you want to, and the opponent plays their move and gives lets you know if it's a good move or a bad move, just like how an environment is, right? So in that case, you don't know the logic behind it, but you experiment, you try random moves and then try to find an optimal value, or then try to find which move was giving you a good outcome and which one was not. So that is model free and model based methods. Now if you see in real life, most of the models which we discuss, RL models, will obviously be model free methods, right? Because they'll use model free methods, because the RL methods which we discuss, they are for huge models, and for huge models you cannot sit and decide the entire logic for the entire game or whatever the model is, right? So we mostly deal with model free methods. So that is something which we have to clear. So again, model based methods are for models which you know all the environment dynamics, right? The transition state probabilities and the rewards, everything you already know beforehand, even before interacting with the environment. But that's not so for model free methods. So first we'll discuss model-based methods, because obviously those are simpler because you know all the things beforehand. So there are two methods which we can use. One is hello, am I audible? Okay, cool. So we'll move on now. Having discussed what model-based and model-free methods are, let's move on. Yeah, okay. So it's time for attendance. So we'll wait for a minute or two. Okay, so I think everyone has marked the attendance. We'll move on. Okay, so as we discussed, we have two types of methods, value iteration and policy iteration, right? So we'll first start with value iteration. So, okay, so now value iteration basically is a method where you find the optimal values, optimal state values, right? So if you have the optimal state values as we discussed, from each state you can know, okay, this state has a greater value, so I should go there. So basically you know which action to choose. So that's how you can solve that problem. So in value iteration, our main focus first is to find the optimal state values. So how do we do it? Now, we have no clue at the beginning. We have no clue what is the value of this state. So we calculate it, right? So we assume that each state value is zero for all the states, right? Hello, am I audible? Okay, so we'll continue. And so as we discussed, value iteration main focus is we need to find the state values, optimal state values, right? So we'll look into this algorithm, which is there on the which you can see on the page later, but we'll move on with the procedure first. So moving on to the next slide. Yeah. So we'll first consider a simple game. Okay, so let's actually have a realistic example here. So let's say we have some superhero who's trapped in some grid, right? Some 12, 3x4 grids. There are 12 cells here, and one of them is blocked. So the black one is basically not a state. You cannot enter there. So we have 11 states here, 11 cells, okay, in the grid. Now, let's say our superhero needs to reach the green cell so that he can get out of this grid. So this grid is like a trap, and he has to reach the green cell, which is the exit. Okay, and but if he reaches the red cell, there's a death trap over there, and he'll die. Okay, so basically, all he has to do is avoid the red cell and reach the green cell, right? So if we view it in a way in an RL model situation, so we have how many states here? How many places can the agent be in? It can be in 11 states, right? So it's a 12, it's a 3x4 grid, and one cell is not valid. So we have 12 minus 1, so 11 states, right? And how many actions can you have? The maximum number of actions that you can have in one particular grid, one particular state. So you can either go up, down, right, or left, right? So these four places you can go one by one. So basically these are the four actions which you can perform. Now let's say because we have to train our agent to reach the green one, we'll say that when the agent reaches the green cell, we'll give him a reward of +1. And when he reaches the state of red cell, we'll give him a reward of -1. Okay, so that way we'll find out which the agent will be able to find out on its own which state is the best state. So I hope the game is clear to everyone. So it's 11 state game. We have four actions and +1 -1 reward, right, for the green and red cell respectively. So moving on. Okay, so as we had discussed, the first and the foremost thing which you should do is randomly allot all of these cells to zero, all of these states to zero, right? So here, that's why the number on each cell in all the other slides also, the further slides also, the slides which will come up, it will represent the state value, right? So here, the state value has been allotted zero, has been assumed to be zero for all the cases in the beginning. Now, as we will train our model, it will get finer and finer. So moving on. Yeah. So now the next thing that we do here is, okay, so we have our state values now, and now we need to update our state values to finer and finer values, right? So one thing which we can do here is, because we have a state value now, but it's not optimal. Obviously, it's not the correct state value. It's a randomly allotted state value. We need to make it optimum. Now, to make it optimum for a particular state, we should find out, okay, so which action should I take to such that it'll have the maximum amount of return. So like for a particular state, suppose you're in a state S, right? And now you have three actions, A1, A2, and A3. Now you need to find out, okay, if I take A1 action, what is the reward? What is the return? Basically, what is the Q value? So for S comma A1, what is the Q value? Okay, fine. So this is the amount of return I'm getting. S comma A2, same, similarly, we'll find some amount of return, right? The Q value. So we'll calculate the three Q values in this case. S comma A1, S comma A2, S comma A3, right? Because Q value is defined for state action pair, right? Obviously, as we discussed. So, okay, now if I find out the three Q values, can I say something about the state value, optimal state value? What I can say is the maximum amount of Q value out of the three values, the maximum should basically be our optimal state value, because that is the maximum we can achieve in that particular iteration. In that particular iteration, that is the maximum we can achieve. So we can basically update our state value from the initial value, which was randomly allotted, to the next value, right? So like this, we can keep on, we can go keep on iterating. So this is what basically is Q value estimation. Now let's take a particular state 1, 3. Basically, this is this cell which is immediately left to the green cell. Okay, take that particular state. Now think of what actions. Okay, that state our state is fixed. Now think of what actions we can perform on that state. So now we can definitely not go up because there's no up defined, right? That's the topmost layer. Now if we can go down, we can go to the right, and we can go to the left. Those are the three possibilities. Now we have to check which one will give me the most optimal answer, right? So what I'll do here is we'll take the three actions one by one. So for the first one, I've written 1, 3, right. That is, we are in the state 1, 3. That is the again the cell which is immediately left to the green cell, and we are moving to the right. Okay, so uh, I have I have written I mean we have decided, the agent has decided that we have to move to the right. But again, we know that the environment can, depending on the transition probabilities, it can send us to the right or in other states as well, right? Because it's not a deterministic model. We are assuming it's not a deterministic model. If it's a deterministic model, things become much simpler. But in this case, it's not. So what we'll do here is we'll assume that 80% of the time the environment listens to us. That's our assumption. Okay. So, and the other 20% will do random stuff. So it'll take random actions. So now for the right one, I've taken 0.8 into something. And then I've taken the other, for the other two terms, 0.1 into something. So as Pranay had discussed the expectation value thing. So basically I've used that here, but again, we don't need to go into the math. We can use the Bellman equation directly. So two slides back, we had discussed the Bellman equation. We had seen the Bellman equation on the slide. Basically, we're just blindly using that equation, putting all the values, because we have everything, again, because this is a model based system, right? So we have all the values available to us. Uh, we'll just insert these values and get our value. So get our final value, the state value, updated state value. So for the first one, 0.8 times it will go to the, 0.8 is the weight attached to actually moving right. And if you actually move right, the reward will be 1, right? The reward which you will get is 1. So that's why it's 0.9 times 1. Again, here 0.9 is our discount term, which we had discussed. All of this, I will not explain the math in detail, because again, we don't need, we are discussing the algorithm here, and we don't need to delve into the calculations. All I'm doing here is, two slides back, there was a Bellman equation, and I'm directly inserting those values and directly getting my final values, final state value, updated state value, right? That's all I'm doing. So for 1, 3, right, down, and left, I'm getting the values as 0.72, 0.09, and 0.09. Okay, so what does this say me? This says me, this says to me, if I'm at the state, if I'm at the state 1, 3, which is again the cell immediately left to the green cell, if I move right, my state value, sorry, my Q value is 0.72. That means I can get an expected return of 0.72. If I choose the action of going down, my expected return is 0.09. And if I choose the action of going to the left, my expected return is 0.09 again. So obviously, if you have to choose the optimal action, you'll choose the 0 points, the one which gives you 0.72. So that's why the state value of 1, 3 after updation is 0.72. I hope that's clear. Basically, all we're doing is finding all the various actions that are possible here, plugging the Bellman equation into it, plugging the values into the Bellman equation, and finding the maximum value, right? So here we can see that after this iteration, if we move to the next slide, we'll see that the state value has been updated to 0.72. Yeah. Pranay, slide before that. The slide before that. We yet to discuss that. Yeah. So this basically, as we had discussed, after finding the step, our step 2 was Q value estimation, right? Now we'll move to step 3, which is state value updation. Now, after estimating all our Q values, what we did here is we got 0.7 to 0.09 and 0.09, right? So we'll update the state value with the maximum value of that. So moving to step 3. Yeah. So state value updation. So as 0.72 is the highest, we can update the value of state 1, 3. Sorry, not state 3, state 1, 3. There's a typo there. State 1, 3 as 0.72. So that's basically all we have to do in this algorithm. We have to just keep on updating. Now here I have done only for 1, 3, right? Like this, you have to do it for all the available states. So all the 11 states, if you do, you'll find that after the first iteration, all the other values will come out to be 0 because we have no, because basically 0.72 the value we got because of the reward one, which is immediately right to it, right? But for the other cells, they most of the other cells don't have any reward adjacent to them because there are again gray cells only. So that's why their values will again come to be 0 in this particular iteration. Again, we don't need to know that. We'll just use math and find out the values, right? So that's all we are doing. So basically, the table, the grid on the left in this slide is the state value function which we'll get after the first iteration, right? Now, if I similarly do the entire algorithm again, I'll get to the state value function, which is to the right. Okay, so here you can see that the value 0.78, 0.72 has been updated to 0.78. Now, if you see, in the first iteration, we saw the 0.7, the change was from 0 to 0.72. That's a large change, right? But in the second iteration, it's only 0.06. So there's one thing we can note here, that the changes are getting smaller and smaller as we go further in the iteration. That is what basically this algorithm is all about. Okay. So now if we check the other two cells which has been updated, the cell which is 2 cells to the left of the green one is 0.52 now instead of 0. And the cell just below 0.78 is 0.43. So now you can see that, okay, fine. Why is the 0.43 cell having a lesser state value? One way to think about it is because it is immediately close to the red cell, right? So that is one, that can be one reason. And also the obviously 0.78 should be higher because it's very close to the green cell. 0.43 is 2 steps away from the green cell. So in a way, it also makes sense. It also makes intuitive sense why this algorithm is working, right? So now we do this, we keep on repeating and repeating, but when do we actually even stop? So after a few values, actually not a few values, after a couple of values, we'll say, not to mention how many, it depends. So after a set number of values, we'll see that the state values are not changing much. So here we could see that the change was 0.72 in the first iteration, and after that it was 0.06. As we move on and move on and on, we'll see that there will be a iteration where the change will be negligible. It will be in orders of 10 power minus 6 or something, right? So obviously that we don't need to get that optimal, so we can stop over there, and that will be our optimal state value function. After that, if you keep iterating also, the value will basically not change at all. The change will be negligible. So that is when you'll realize that you have reached the optimal state value function. So I hope this algorithm is clear. I'll just give a quick recap. The first step was obviously we'll initialize all the values to 0 or any random value for that matter. Step 2, for a particular cell, for a particular state, we'll find out the maximum Q value it has for all the given actions for that state, right? We'll find out the maximum Q value, and that value will be updated as our state value for that state. and that will do for all these states in one particular iteration. That's one iteration. Then as you keep iterating and iterating, you'll find out that the state values after a set number of iterations, they don't change at all or negligibly change. So that is when you find the optimal state value function. So now that you have found the optimal state value function, we can very easily determine the optimal policy, right? Because if we have a state S and it has two actions, and those two actions can lead either to state S1 or S2, the state which has maximum state value among the two, S1 or S2, the greatest state value, we can directly say that we should take that action which will lead to that state value, right? So this way we can directly associate each state with a given action such that it will take us to the state with the maximum state value. So that's all we are doing here. So after finding the state value function, we'll just update the we'll just update the policy also. So at the last, after one policy updation, directly we'll find the optimal policy because we have the optimal state value functions. So moving to step 4. Yeah. So now with our optimal state value function, we can easily find a deterministic policy. Why is it deterministic again? Because like we already know that from a given state, what is the which state will give you the maximum state value, right? So you always take that particular action only. You won't think whether should I take this one or that one. You won't double think of it, right? So you'll always take that particular action. So that is why it is called a deterministic optimal policy in this case. So I hope value iteration is clear to you all. Okay. Now that we have discussed value policy, value iteration in such, it is similar to value iteration, but in this case, okay, in value iteration, we only took a random state value function, and at the end, we using the optimal state value function, which we found out, which we calculated, we found out the optimal policy, right? But here, we will actually first take a random policy. What do I mean by random policy? So suppose for a given model, if I have any particular state S, so I'll randomly allot, okay, if this is the state, then I'll take action A1 because I don't know anything about the model yet. I have not calculated anything, right? So I'll just randomly allot a policy. So that is the first step in policy iteration. Okay, so policy iteration mainly has two steps: policy evaluation and policy improvement. So these two steps will be repeated in loop till we find an optimal policy, right? So we'll discuss how we do that. So moving on. Yeah, so first basically known is basically known for doing this particular operation, which is finding the state values given a policy. Now, if I have a particular policy in mind, if I know what action will do what, right? So directly I can apply my Bellman equation and use it to find the state value, right? Now I don't need to check the Q values and find the maximum, all of that we did in value iteration, because I already have a policy with me. Though it might be a random policy, it might not be optimal, but for that particular case, we're using that policy. So even though I have a policy, I can directly use it in the Bellman equation, and I can find my state values for all the states, right? So we can find the state values for all the states. Okay, so now in one step only, I have all the state values, right, for that given random policy. But we know that this policy is not optimal. It is a random policy, right? So obviously the state values are not optimal because it's coming from a random policy, comes from a random policy. So what we'll do is we'll try to update our policy. Now, how we do that is we have an example over here. Let's say you can see the image in the left, which has which has 6 states, S1 till to S6. Now, suppose and there are 2 actions in each one. It has 3 actions in 3 of the states, and the other 3 states, S4, S5, and S6, are terminal states. That means they don't have any action. They directly have just a reward. That means they will end the episode. They'll close the game or whatever the model is, right? That will be the end of the game. So now let's say we have a policy that for S1, S2, and S3, I'm taking north direction instead of south. It's a random policy. I don't need to check if it's correct or not. I'll just keep it like that as of now, taking the north action. Now, Okay, the second image is the transition probabilities. Again, that's for math. You just need to plug it into the formula. You don't need to actually sit back and find the values of something that will be given to us again, because it's a model based system. We have the transition probabilities with us. So here we're assuming these are the transition probabilities. Now when we use this random policy and we apply Bellman equation to it, you can see that towards the right there are six state values, and these are the state values for that particular policy, which is always going north. So v of s1, s2, s3, s4, s5, s6, all these values we can easily calculate in one iteration only for that random policy. But again, we know that this is not the right one, right? So we'll move on to the next step, which is policy improvement. The next slide. Okay, before moving to the next step, let's have attendance. Meanwhile, does anyone have any doubts? Okay. If you have a doubt, please type it out in the chat box so that I can unmute you and we can have a discussion. Yeah, so I think we can continue. So moving to the next slide. So till now we had discussed how we took a random policy, and based on that policy we found the state values, right? Till now that we have discussed for policy iteration. Now we know that these are not the optimal state values because our policy was completely random, right? So now what we'll do is something known as policy improvement, basically improving our policy. Now what I'll do is, so we know that using the Bellman equation, we can basically we have the state values, right? Now for those state values, suppose again, let's take a simple case of S1, S2, and S3. Suppose I have a state S1, which is taking which from some action is taking me to state S2, and from some other action is taking me to state S3. Right now, all these state values we have now because we had the random policy with us. So now from that state S1, I can choose which policy I have to I mean, I can choose which action I need to choose based on the state value, right? So again, for each state, I can have a particular action which I can think of because we have the state values. All we have to remember now is that we have the state values. So for each particular state, I can choose which action should I take so that so that I choose the state with the maximum state value. So that means again we have a new policy here. Why new policy? Because we are able to choose which action from which state. So this basically becomes our updated policy. Now, if you see in this particular case, so we had seen that using our Bellman equation, we can find out the state values, right? So using those state values, again, if you find the two actions north and south. Now, if I find the for state S1 and action north, if I find the V of S, which is basically if I take S1 and take the north action, it will take me to some state, okay, and that state for that state, the state value is 1.8, and if I take south, the state value for that state is 1.2. So obviously we'll take north in this case because it's giving me a greater state value, right? So I'll take 1.8 here. So I'll take north here. But if and this actually agrees with our original policy also, which we took randomly. But and that happens for S3 also. But if we take S2, here in this case, for south we are getting 0.4 and north we are getting minus 1.4. So obviously in this case we should choose the south action. Okay. So we basically update our policy. Our initial policy was n comma n comma n, north north north, but now it is north comma south comma north, right? So we updated our policy. So this is basically policy improvement based on the state values which you calculated before. You can find a new policy, and that new policy we basically iterate over many iterations till that new policy also begins converging. So basically here we have only three, right? So after so in this case it will take less iterations, maybe some 10 iterations, and the optimal policy will not change at all. So if it's n comma s comma n, it'll keep on staying n comma s comma n after 10 iterations or something. But if you have a large model, it'll take large number of iterations, obviously. So that is the thing. So basically what we do here is we take a random policy, and based on that random policy, using Bellman equation, we find our state value function. Now, using those state value functions, we know that if we have state values, we can make another policy which will basically point me towards the state with the best state value, right? With the greatest state value. So we can do that as well, and we'll find a new policy, and we do this loop again and again: policy, state value, policy, state value, again and again till we find an optimal policy. So here, what we're doing is we're repeating our policy function again and again and again and again. So we are basically reiterating our policy, finding our optimal policy again and again. But in value iteration, we had to do that only once at the last because we first found the optimal state value, not some random state value, right? So that's the thing with policy improvement. So policy improvement, it has two main steps which are being repeated over and over again. So that's about policy improvement. So moving on.
I'm sorry, we have run into a technical issue. We'll try to fix it as soon as possible. Until then, if you have any doubts, please write it on the Q&A page. I'll unmute you and you can ask the same. You can also ask questions on the Slido link shared. We'll reply to questions there too if you're having some audio issues.
Hello, am I audible? Okay, cool. So I think the technical issue has been resolved. So um, sorry for the inconvenience, and we'll be moving to the next algorithm, which is Q learning. So what Q learning is all about is it's basically the most fundamental algorithm which you'll use for all the RL networks which are actually used in real life. Because again, as I discussed, value iteration and policy iteration are for model based solutions, right? So when you have a clue of what the model is eventually doing and whatever the transition probabilities are and the rewards are, everything you know. Okay, so in that case, you can use value iteration model, I mean policy iteration. But as we've already discussed, this is very improbable to know the entire structure of the model when you have actual, deep RL cases. So in those cases, you need to jump into Q learning. So Q learning is an algorithm which is similar to the two we discussed a bit before this, but there's a catch here. Here you don't need to know anything before. You can just play with the environment, interact with the environment, take random actions, and find out the optimal solution. So this is actually very non-intuitive if you think about it. Like you're just making random moves, and you find out what the optimal solution is, right? So it's like a toddler playing chess, but without knowing the rules itself, it is able to win. So basically, that's what it is. So toddler cannot do that without knowing the logic. So we know the logic, but the computer does not need to know the logic here. It is able to learn on its own. And that is what is machine learning, right? So this is one wonderful thing here, Q learning. And this is basically uh, a stepping stone to all the, higher level of RL networks. You have um, policy gradient and stuff like that. And Q learning is the most fundamental thing you'll and it'll be used for deep Q learning as well. So there's another higher algorithm called deep Q learning and stuff like that. So Q learning is the fundamental thing for it. It's a building block for that. So we'll move to the next slide. Okay. So Q learning is a popular model free reinforcement RL algorithm. And here we find an optimal policy without requiring the environment's dynamics. So quite interesting. So how does it do that? Um, Before jumping to that, I think we should have our quiz now. Just a minute. Yeah. So if you're all able to see the screen, you can join the Slido quiz and give your responses. I'll activate the poll. Oh, sorry. Yeah, so this is a I won't say tricky, but it requires thinking. So I'll give it some time so you can answer. Yeah, so I think that's enough time. Yeah, cool. So okay, so this is actually uh, the answer which has been marked the least is actually the right answer in this case, because obviously I expected this because this is a tricky question. So oh, so not the least, the second least. Okay, fine, that's still better. Okay, so mostly we deal with model-free algorithms in real life. That is actually true, right? Because as we had discussed, for complex models, we cannot find the entire logic, right? We cannot, because the logic is so complicated, we cannot depend on value iteration and policy iteration, right? So that is why we deal with model-free algorithms in real life, because we can't use them because they are very complicated, right? Because the RL models are really complicated and you can't always find out a proper logic to them, right? So that is why that is the reason why Q learning is very important, because it deals with model-free algorithms and not model-based, like the two we discussed before. And policy iteration alternates between evaluation and improvement of state values. That's the catch. Actually, it does alternate between evaluation and improvement, but not of state values, of policy values. That's the thing, right? So it's improving the policy, evaluating the policy, improving it. So that's what is happening. That's why. And the other two, I think, are pretty obvious. Policy and value iteration need to have details of transient probabilities, yes, because they are model-based methods. And value iteration calculates optimal policy only at the end. Yes, as we discussed, policy iteration is alternating, but value iteration does not alternate. It find the optimal policy only at the end after optimal state values have been found out. Okay, so I think we can move to the next, the most important topic, Q learning. So now Q learning, basically, again, we have no clue about what the environment is doing, right? So we need to randomly initialize something. So if it's Q learning, obviously it makes intuitive sense to start with Q values first, because they will tell you what action will lead to which state and how good it is, right? From a particular state. So we'll initialize our Q value table, something known as lookup table or Q value function. Both are similar terms. So here again, to explain what Q value table or Q value function is, we have a scenario here. We have a 3x3 grid, and from each grid, I mean from each cell, we can either move up, down, left or right, right? So there are 4 actions here. So in total, there are 9 states because there are 9 cells here, and we can move to we can from each state we can take a maximum of 4 options. So now obviously if you take the topmost and the leftmost cell, it cannot move left or up, right? But still we'll include that in the queue table and mark it as 0 always. So that's what we're doing because that action is invalid, right? But still so whatever the maximum number of actions is for a particular state, that time that multiplied with the number of states we have is the total dimension, the total size of the uh, Q value lookup table. So here you can see there are in total 9 states, 1,1, 1,2, 1,3, and there are so there are 9 rows here and 4 columns, left, right, up and down, right? So basically initially these are the Q values and we are uh, uh, equating all of them to 0 initially. So that is what is happening here. And that is a pretty straightforward step. We don't need any explanation for that because we don't know anything. We'll just randomly allot 0 value to them. Next, moving to, okay, now we have to find the Q values, right? So for Q learning algorithms, we know that we don't have the environment dynamics before us. So we need to actually explore the environment. We need to take a particular action and find out what reward we are getting, to learn, okay, this action is giving me this reward. So we need to do exploration here. So the way we are going to do exploration here is we have to decide what action to choose, right? So like, how do we can't just always randomly take a particular action and try to learn the model what it is doing, right? So we have to decide which action we have to take. So now how do we choose the action? So that's a thing we have to ponder about. So here we can use the concept of exploitation exploration trade-off. Okay, so it's fancy sounding stuff, but it's not. It's actually very easy. So we'll move to what is known as exploration and exploitation. Now imagine a scenario that you're shifting to a completely new city, all right? And you are a foodie again, assume that also. I mean, most of us are, but assume if you're not. So if you're a foodie and you're moving to a new city, your main concern would be which restaurants here are good so that I can have a good time or have good food over there, right? So suppose there are some 20 restaurants known to you, and before before visiting any restaurant, how do you choose which restaurant should I go? It doesn't really matter, right? Because you have no clue about any restaurant over there. So you need to randomly choose a restaurant then, right? And take a risk and try out a restaurant, any random restaurant, and find out whether the food there is good or not. So this is called exploration, basically. Okay. So now coming to exploitation. Suppose yes, we have stayed in the city for a while now, and you have visited most of the restaurants over there, and you have pretty good knowledge of what type of food is provided where, and you know which food is good, and like you have an idea. So basically, you have an idea which restaurant gets good food. So what do you do now? Now, if you have to choose a restaurant, would you randomly choose a restaurant or would you choose the one which you know gives the best food? Obviously, we'll choose the one which has the best food, right? So that is called exploitation. Basically, after knowing what our model is doing, or in this case, what type of restaurants are serving which type of food, most of the restaurants, if you have clue about, you'll not take a risk of randomly choosing a restaurant and choose the one which you know gives good food. So that is called exploitation. Now, in terms of our RL model, now, at the beginning, as we discussed, we have no clue about what action is going to give you what state value, what Q value, right? So what we do now is, yeah, so we explore here. So now exploring is basically if you're in a particular state and and there's so basically if you explore that state, that means you randomly choose an action. You do not think of anything, you randomly choose an action. So in this case, you can see from S1, you're randomly moving to Q4 state. Okay. Even though Q2 has a higher value, a 1.7 than 1.2, right? Still, you're going to move to Q4 because it's randomly chosen, because you want to explore Q4 also. Maybe after Q4, there's something, the state value, the Q value is very high. The action after Q4, it can be, we need to explore. So that's the thing. So that's why this is called the exploration step. Now, exploitation, once you've already studied about the model, you know which action is giving what, you can directly uh, go to the state with the highest Q value. So in this case, from S1, we are going to take the action A2 so that the Q2 we are getting is 1.7, right? So this is what we'll be doing. Now we know that exploration and exploration both have their benefits, right? Exploration is important because you need to know about the model, you need to learn. And exploration is obviously important because we need to get the best rewards also. So how do you find a perfect balance between two? So to help us with that, we have something called the epsilon greedy algorithm, the epsilon greedy policy in a way. Okay, so this policy, what it does is it there's a number, we choose a number epsilon, okay, and that number is obviously between 0 to 1 because it will represent a probability. Now that epsilon value, it is the probability of choosing a random action. Suppose you're in a particular state and you need to decide should I choose a random value or not. So you check the probability. Like you have if the epsilon value is very low, if it's like 0.1, you don't choose a random value. You choose the you take the exploitation value. Basically, you take the best value. You do exploitation. But if epsilon value is high, in that case, you choose exploration, right? You take a random value. So now this is our epsilon greedy policy. We choose a number epsilon, and that number is the probability of going to the choosing exploration rather than exploitation, right? So now initially, as we discussed for say the first episode, we have no clue about what the algorithm is, what the model is doing, right? So obviously we need to explore more. So that's why in that case, epsilon should be close to 1 because for a good model, obviously, because in that case only we'll be able to explore more. But if as we go further and further and we learn much more about the environment, we'll obviously choose to exploit. We'll choose to maximize our rewards. So in that case, epsilon value should be low because we don't want to take random values. So that's the thing with epsilon greedy. So in this case, we can see here that at the beginning you have many you have epsilon value to be high because it's close to 1 year, and as you go further and further, it is decaying down to 0, right? So that is our epsilon greedy algorithm. So the number epsilon that we are choosing, basically you can choose it from this graph only. We take a function like that, epsilon function, and as the episode gets higher and higher, as you learn more about the model, the epsilon value will reduce. So that's the epsilon function you choose to you choose, so that because that will give you the best solution, right? Because intuitively also it makes sense. So yeah, so that is the epsilon greedy policy. And exploitation and exploration, these two, this is very important for Q learning specifically. Okay, now we go to our step 3. So step 2 was all about action, right? So we know what action to choose now, right? Because from our epsilon greedy policy, we know what action to choose. Okay, so now we have a state, we have a particular action. Now we can directly calculate the Q value, right, for that particular state and action. But if you think about it, there are two ways to do that actually. One way is directly, you have a Q lookup table with you, so you know the Q value already. I mean, you have assumed it earlier, but still, in your data set, you have in your database you have a Q value for that particular state and action. Okay, so that one thing you already have, but we can also calculate it in another way, right? So what you can do is, if you look at the image from state S1, you take the action A1 and get reward R1. Okay, fine. Now from state S3, if you take a particular action A3 and take the Q value for S3 comma A3, this will give you the entire expected reward for the next part of the um, uh, action set, right? So whatever actions you're going to take. So for all those parts, you can directly say that the expected reward is going to be Q3 comma A3. So basically, if you add R1 to that, you'll end up with the Q value for S1 comma Q1, S1 comma A. Yeah. So if you add R1 and add the Q value for the next state and an action, you get the Q value for the original state and the action. So in that way also you can calculate, but there's a catch here. Because we are taking from the next step onwards, we have to add our discount value, right? From the Bellman equation as we had seen. So if you see over here, we can say that the Q value should be reward plus gamma times maximum Q value. Why maximum again? Because we are trying to find the optimal Q function. So for that, we try to find the maximum Q value. So let me explain it from the diagram again. Suppose you're at state S1 and you want to find the Q value of S1 comma A1, not directly from the lookup table, but using S3's value. So from S1, you're taking A1 going to S3. Cool. Now from S3, you have let's say from S3 you have this action A3, and this action A3 is the action which gives you the maximum Q value from S3, right? and you take that action, obviously, because here we are trying to find optimal one. Okay. You keep you for the calculation of S1 comma A1, you use S3 comma A3 Q value. Okay. So you can directly write Q of S1 comma A1 is R1, which is the reward from going to S1 to S3 plus gamma times of Q of S3 comma A3. Right. So you can directly say that. So you can look from here also. The equation has been given below. So this ideally should be our value of Q of S1 comma A1. And now our value, which we already have, right, which we already have from the previous, from the lookup table, those two values should match, right? Because these basically are calculating the same thing, Q of S1 comma A1, right? So these two values should definitely match. Now, they obviously will match if our Q value function is optimal. But in this case, as we started from a random one, from allotting all zeros, it obviously won't be equal. So we need to, so there will be some error, right? So there'll be some error. So this error can be determined like this. So this basically the LHS in this equation, the last equation in the image below, R1 plus gamma Q of S3 comma A3. So this particular term is the return which should be from the estimate from the next state. So what we just discussed. And if we subtract the value which we have in the lookup table, these two should subtract, and the difference between these two should be the error. So this we have to minimize, right? Because it should be close to zero. So what we essentially do is we update our Q values now. So basically, so for Q of S1 comma A1, we have we need to make it we need to reduce the error, right? So we need to add the error term to Q of S1 comma A1 so that it becomes equal to the next state, right? So here, if you look, Q of S1 comma A1 is equal to Q of S1 comma A1. You're taking that value and adding the error term to it with some alpha factor, which is the learning rate, because you don't want to take the learning rate to be you can change the learning rate. It's a hyperparameter, as we had discussed in the previous sessions. It's a hyperparameter, and based on fine tuning the hyperparameter, you can find the perfect, the quickest model or the most efficient model. So in this case, basically, we're trying to reduce the error, and we are trying to directly, um, we are trying to add the error factor so that the error reduces, right? So like we are adding the error to the wrong value to make it correct, something like that. Again, this is all mathematics. We don't need to delve deep down into this, and we directly have this equation right here. And this is the most important equation in Q learning algorithm. The equation which is there in the below picture, the last one. Q of S1 comma A1 is equal to Q of S1 comma A1 plus alpha times that term, which is the error term, right? Okay. So now if we put all of this together, because Q learning algorithm is the most important algorithm, so we'll just put all of this together. First, we'll initialize our Q value table, right? Then after that, the second step says that we have to choose an action, which we do using epsilon greedy strategy. Then we have the state and we have the action. So we can find the Q value now. When we can find the Q value using two methods. One is directly from the lookup table which we have, and one is using the Q value from the next state, right? So using that, you can find the Q values in two ways, and the error, we'll try to minimize that error, and hence we'll do that repetitively again. We'll do that for all the Q values repetitively, such that the error term will automatically reduce to a very, very low value. Okay. So after that, after that, what eventually happens is we'll reach convergence, and the Q value will not change at all because the error will be very close to zero. So cool, right? So this after that, after Q values stop changing a lot, finally we'll have the optimal Q value function. And obviously, if we have the optimal Q value function, we know what action to choose to get the to get the maximum returns. So we have a policy also. So for each state, we can choose which Q value is the highest, and we can choose the action for each state. So we have a policy. So the brilliant thing here is we have no clue about what the model actually is doing. We just explored a bit. We just got our hands dirty into the model, and it's able to tell us which thing to do when, right? So that is the brilliant thing about Q learning. So I hope that's clear. So now for Q learning, we have a code implementation as well. We'll just go through it. We're running out of time, so I'll just quickly discuss this. Okay. So here we have our, here we have our imports, import numpy, as we had discussed in the first session. The import gem thing is a very important module for reinforcement learning because it has some predefined modules, predefined models. Like for example, the one we are using here is cart pole. So it has some predefined models, and you can directly use those models to implement your code, right? So here cart pole environment we have, and I'll explain what cart pole environment is. Basically, there's a cart and there's a pole on the top of it. So obviously from physics, you know that if the cart moves here and there, the position of the pole will change. And um, depending on that, the pole will either fall or, you know, try it'll stand. So what we do is we play a game, we randomly move the cart, and we find, and we try to keep the rod state, the stick straight. Okay. So how we do that is, there are many states here, right? The one state would be the angle which the rod is making with the horizontal, and one would be, okay, just a minute. Okay. Fine. Okay. So yeah, so the gym model basically helps us to implement models such as the cart pole, which we'll be using here. Now the cart pole model, it will give us a reward of +1. We are choosing it to give a reward of +1 when it's standing straight, and -1 when it's falling down. So that way it can learn to stand straight, right? And so that's the reward. But now what about the actions? The actions can be +1 and -1. That is the cart moving to the right or to the left. Okay, so that is the way we are defining our action also. And now what about states? So states, we have a lot of states here because we have lots of independent terms, independent quantities here. So one would be the angle with the horizontal, one would be the velocity of the cart, and one would be the position of the cart in itself from the origin, and one would be the velocity with which the rod is also moving, right? So all of those different uh, values we have, and any combination of those will give a unique state to you. So what you do is, obviously, because angle is a continuous thing, right? From 0 to 90 degrees, you have a continuous angle set. But again, for continuous states, we cannot use Q-learning algorithm because it will have infinite states in that case. Because continuity, if I ask you how many numbers are there from 0 to 1, there can be infinite numbers, 1 by 2, 1 by 3, stuff like that, right? So there will be infinite states. So that's why we choose to not use continuous states and we use discrete states. So what we do is we take states like 0 degrees, 10 degrees, 20 degrees, 30 degrees, stuff like that. Okay. And for velocity also, 0, 2, 4, 8, 10, stuff like that. So in that case, it will be easier for us to implement the model because we'll have finite number of states. Cool. So now we discussed about import gem. Import time is the time module which will help us to find out how much time it took for the various operations. Import math and import matplot. Matplot is for plotting, as we know, and import math is for mathematical calculations. So now here we'll be implementing our model, cart pole model, and we'll be finding out how many actions are possible. So we are predicting the number of actions, which is 2 in this case. You can see here, right? So 2 actions, which is moving right and moving left, increasing the velocity in the right or increasing the velocity in the left. And here are our hyperparameters. Learning rate we have taken as 0.1. Discount we have taken as discount factor we have taken as 0.95. Episode 6000. Episode 6000 means how many times do we have to run the code to make it learn, right? Okay, fine. And this observation list is basically the number of the dimension of all the possible states there are. So there are 30 cart position states, 30 cart velocity states, 50 for pole angle, and 50 for pole velocity, as we had discussed. These are the 4 independent terms here. So any combination of all these values will give you a finite state, right? So the number of finite states will obviously be 13 to 13 to 15 to 50 because these many possibilities are there. So again, we don't need to go deep into this. And this function here, it'll try to discretize the values. So whatever angle you're getting, you're trying to find discrete values from that. Suppose if your model is accepting 0 to 4, stuff like that, and if you have velocity is 1.9, it'll round it off to 2 and find and take the discrete value 2. So that's what it's doing basically. Again, these are the hyperparameters, epsilon and all. Here we'll be implementing our Q table. So Q table shape basically is the number of states we have, as we have discussed, the total number of states times the number of actions, the maximum number of actions for each state. So that's 2. So that's why we have a Q table of these many dimensions. Okay, so fine. So this is our function get discrete state. Again, this will just be implemented in the main code to find this get the actual state state array, the the 4-dimension array which we had 30, 30, 50. So which particular value is referring to what? Which particular state referring to what parameter of that particular uh, property? What is the cart position? What is the cart velocity? Stuff like that, right? So okay, so now here is the main code. Here first we are using epsilon values list, and we are having it as 0 because we haven't decided any epsilon yet. But as we use our epsilon greedy strategy, we'll find the epsilon values will go decreasing, and we'll see that now. So we have discrete. So we have all the number of episodes here, and for each episode we'll be repeating this code, right? So what this code essentially does is we have discrete state, and this is basically the 4-dimensional matrix I was talking about, which will tell you what state your particular agent is in, right? Now, if you take a random epsilon, right, and you choose a random number, if that random number is greater than epsilon, you will choose to basically you will choose to exploit, otherwise you'll explore. So this is basically what our epsilon greedy strategy is. Again, this is math, so you don't need to go into that. This is basically our epsilon greedy strategy we're using here. And here, when you apply this function called dot step come an action, this will help you to get the next state from particular action, the reward, and whether the episode is done or not. If the episode is done, this done value will be true, or it will be false. And here you can get the new discrete state out of the new, you have the new state, right? So you can get the discrete value of that also, the 4-dimensional matrix for that also. And then you, okay, the main formula is here, yeah, the new Q value. So you have as we discussed that you take the Q table and you find all the possible actions for that next state. So this is new discrete state. So in the Q table, you search for the new discrete state. Okay, this is the new state, and you find the maximum value of among that. So that's why np.max, and that will be your maximum future Q, right? And if you directly apply that into the Bellman formula, which we had discussed, this is the formula for Q learning, which we had discussed. So new Q is equal to 1 minus learning rate into this plus learning rate into this, right? So this is basically the error term. Reward plus discount times this. This is the error term, right? This times learning rate will give you the will basically tell you what you have to add to the current Q. Oh, basically they have manipulated the formula a bit. Basically, this term, if you combine it with this term, the learning rate into current Q, if you combine it with here, you'll get the actual error. So it's just a mathematical manipulation, but it's the same thing. So this is the formula. Now, again, in the Q table, you update your new Q value, and then you do that again and again and again and again. So you repeat it till these many episodes, basically. And again, epsilon value, you choose to you want to reduce it, right? So you take the epsilon value and multiply this factor. This is a decay value. This will be less than 1, so that your epsilon keeps reducing each and every time, right? So that's what you're doing, and this is basically what this function will do. So now if I plot the epsilon values, you can see that it starts from 1. Why does it start from 1? Why do we choose it to start from 1? Basically, because we want initially there should be no exploitation, because we don't know anything about the Q values, right? We have taken random values. So that's why we first only explore. And then as we start learning about, as we increase the number of episodes, as we start learning about the model, we decrease the number of, we decrease the epsilon value. Okay, so that is about the code. Okay. So just a minute. Okay. So with that, we come to the end of today's session, and in fact, the end of the AI Club Summer School program. It's a big moment for all of us, obviously, and all I need to say is I need to thank all of you for staying put till here and staying focused instead of all the odds. There were technical issues and stuff like that, but still you guys stayed. So a big thank you for that. And what we actually want to be the main takeaway from this summer program is not this theory part, but we want to essentially instill a sense of interest in artificial intelligence in all the various fields in which artificial intelligence can be applied. So we hope we did a good job with that as well. And okay. Yeah, I can stop sharing the screen now. Yeah. So just a minute. Yeah, so does anyone have any doubts? I think we should be taking doubts now. Anything, you can just put in the chat box or anything. Okay, so you can also raise your hand. I'll allow the mic. Okay, I think there's some issue with chat box. So if you're raising the hand, I'll try to unmute you all. Okay, so I see some hands raised. Kavita, I've unmuted your mic so you can express your doubt. Anything? Okay, cool. Just a minute.
Alright, so around everyone who's raised their hands, mic access, you can unmute one by one and like ask your doubts if you have any. Kavin, Ashwin, Sanjay, Kanchan, Surya, anyone can like unmute themselves and ask your doubts. If due to a technical difficulty you're not able to unmute, then you can text us on the WhatsApp groups and we'll try to address your problem.
Hello, am I audible?
Yeah, if you could be a little louder.
Yes. So, for discussing about
Sorry.
AI and ML. Hello, can
Yes,
you
yes.
hear me?
Sorry, that's better. Yes, that's better.
Yes. So, I am just a beginner getting into this field. Regarding the task too, I find some difficulty how to submit for the Kaggle competition. So, any guidance or any material so that I could study and submit.
You're facing a difficulty in submitting task too, is it?
No, no, to perform the task itself.
Oh, all right, all right. I will ask my heads to provide some material about the same. So I guess they'll get back to you via WhatsApp. Like they'll attach a little bit of material for the same. If not, I mean, worst case, you can go online. There are a lot of resources available for all of these topics. So you can go online and read over the same. But yeah, we'll be sure to get back to you with some relevant resources too.
Thank you.
Anyone else? I've given mic access to everyone who's raised their hands so they can unmute themselves and ask doubts if they have. Alright, so maybe you're facing some technical. Sorry. Yeah. Surya. Uh, Sorry, your voice isn't very clear. Alright, so maybe due to some technical difficulties, you're not able to unmute. In any case, if you do have any doubts, please feel free to contact us. All of us are admins of the WhatsApp groups, so you can DM us and we'll We'll reply to you anytime. So I guess that wraps up the summer school. Thank you for participating and all the best for all your future AI/ML projects. Thank you.
Yeah, we hope we could instill a sense of importance of AI in everyday life for all of you. So, and for latest AI updates, we know that all of this is going too fast. I can understand with Chat GPT and many other AI tools with us, who it's a bit hard to be updated with the latest AI trends, if I may. So for that, we have an AI Club Instagram channel and YouTube channel as well. So you can definitely check them out for the latest updates. And all the best for your AI ML journey to everyone. Thank you.